In this lab, you will determine the solubility product constant, Ksp, as well as the solubility of calcium ion and iodate ion in the sparingly soluble solid calcium iodate. The way you will perform this is by utilizing a titration of the iodate ion with the thiosulfate ion, the sodium thiosulfate. From there, you will determine the solubility S, and from that solubility S, through a series of titrations, you will determine S and then plug it into the Ksp equation to determine the solubility of calcium ion and iodate ion. Remember, in a Ksp, a sparingly soluble solid is in an equilibrium between the solid and its aqueous components. So the Ksp equation is just like the same as in the equilibrium constant that you've performed before, except we do not include solids into our equilibrium expression. You begin by actually preparing your sparingly soluble precipitate, which is your calcium iodate. To do that, you will mix 20 mils of 1 molar calcium nitrate. Remember, all nitrates are soluble, so it should remain nice in solution, and it is. And you will react that with 50 mils of 0.2 molar potassium iodate. The calcium ion here will react with the iodate ion. Remember, potassium iodate is also completely soluble. The calcium ion here will react with the iodate ion here to give you calcium iodate. However, as you know, this is sparingly soluble, and it is in an equilibrium with the calcium ion and the iodate ion. I have already put in the 20 mils of calcium nitrate. Here's my 50 mils. We should expect a precipitate to form, and we'll stir it with a stir bar and let it wait for about 30 minutes for the precipitate to settle. So as you pour this and you use a glass rod to stir this vigorously, you'll see that the solution starts to turn cloudy. Let that sit and proceed to the next steps in the experiment. Before you begin assessing the solubility of calcium ion and iodate ion in calcium iodate, the procedure asks you to perform a standardization. In order to do that, you'll have your titrant, the substance that fills the burette, with sodium thiosulfate. Now, the approximate concentration that's given is 0.025 molar, but that may not be the exact concentration. So the purpose of this experiment is to perform an exact determination of the concentration of 0.025 molar sodium thiosulfate. And that process of determining the exact concentration is known as standardization. So in your titrant, you'll have your thiosulfate, your sodium thiosulfate. Your titrand, the substance that's going to be in your flask, will contain 20 mils of water. It will contain 10 mils of this potassium iodate, and that is something you want to pipette. So you want to use an exact volume. So for exact volume, you'll use this volumetric pipette. You'll also put into this Erlenmeyer flask a little bit of this potassium iodide pellets. The purpose of the potassium iodide pellets is to generate I2, molecular iodine, in conjunction with 20 drops of HCl. I2 that's generated by the reaction of these potassium iodide pellets with potassium iodate in acidic media actually generates molecular iodine. The molecular iodine will react with the starch that you add later on in your experiment during the titration, approximately 40 drops or so of this starch.
After you add the 40 drops of starch to your flask, you will start to have a yellowish-brown color. The addition of the thiosulfate to the molecular iodine will react and thus remove this color.
So what I'm going to do now is I'm going to pipette my 10 mils of potassium iodate, put in some of my pellets, and put in about 20 drops of the HCl according to the protocol, and then I'll begin my titration. All right, now we're ready to perform our titration. In this case, we are standardizing the thiosulfate solution in the burette. If you can focus here on the titrand, the material that's at the bottom of the flask, I've added my iodate, potassium iodate. I've added my potassium iodide, the Ki, and in acid, the potassium iodide pellets have dissolved. The potassium iodate has reacted with the potassium iodide to give you I2, and this I2 molecular iodide is going to react with the thiosulfate. Now, the equivalence point occurs when exact volume of the thiosulfate, the exact volume of thiosulfate reacts with all of the molecular iodine that's produced here in the reaction that was generated in the flask. So to get the equivalence point, we had to calculate that using pre-lab question 4. The protocol says that you're going to go 2 mils minus that equivalence point value that you calculated stoichiometrically. So I'm going to do that. Before you actually perform this lab, you want to do the stoichiometric calculation to determine how much of this reacts with this. But you're not going to put the entire equivalence point. You're going to go 2 mils minus that equivalence point and then go very, very, very slow so that you can get an exact reading. So I'm going to do the titration now, and since I've already calculated how much thiosulfate I need to react with the iodine that's generated in the flask, I'm going to go 2 mils minus that equivalence point. So this is easy. I can just let this go. Let's just stir this, keep it stirring. I don't know if you can see this. Zoom in here, going towards the bottom. So as I am pushing this 2 mils below the equivalence point, I am stirring here. Remember, titrations can be very exact, but the dispensation of the burette is not exact. Okay, there. This is 2 mils prior to the equivalence point that I've calculated based on stoichiometry of the net reaction. Now I will add some drops of starch. All right, I've added my drops of starch. I just went ahead and added some extra drops. The protocol called for 40 drops, so I went ahead and put in 40 drops of the starch. Let us go drop by drop. Okay, this is what's called the exact point in our titration. So this is where you want to have a fine tune and just go 1 drop by 1 drop. So let's go ahead and do that. Be very, very patient when you do this, drop by drop. As you can see here, my yellow is really getting more fainter and fainter. So this is where I really want to fine tune. All right, so I'm almost there. A couple of more drops. I think that represents the total amount of thiosulfate that I dispensed reacting with all of the molecular iodine. The starch color has disappeared. And now I'll just read off the burette. Since I started off at 0.00, all I can do is just go all the way down and read my volume. You want to do this twice. So let's go ahead and repeat the experiment one more time. And that volume that you got the first trial should equal, within reason, to the volume you get for your second trial. So make sure you do this in a duplicate. Concurrently, while you're doing the standardization of the sodium thiosulfate, it may be a good idea to commence preparing your calcium iodate precipitate for the second and third round of titrations. So here's our precipitate. We've let it sit out for a while. Once you have the precipitate and it's settled like this, it may take maybe 10 minutes or 15 minutes, go ahead and start the filtering process. So we'll just filter by gravity filtration. Get all that water out of there first. If you have a spatula handy, you can get a spatula to get the remaining part of this solid calcium iodate. So it's worth remembering that this is a sparingly soluble precipitate, so it's not 100% a precipitate. this precipitate is in an equilibrium with its component ions as well. So for all of this remnant stuff that has stuck to the side of my beaker, I can just do a little deionized water mix and get that in. Maybe one more round. That is finished filtering. You're going to split that precipitate into 2 beakers. One beaker will contain 40 mils of deionized water. The second beaker will contain 80 mils of deionized water. I've collected my precipitate of calcium iodate. So I'm going to split this into thirds. So get a nice spatula and just I split it into fourths. And I will take one little chunk and put it into a beaker that has 80 mils of DI water. And I'll take the second chunk and put it into my beaker that has 40 mils of water. So I'll add a little bit more here, a little bit more here. Roughly equal amounts that you want added to the beakers. Stir it with a glass rod on each beaker or in each beaker. And it's going to take about 30 minutes or so for this precipitate to settle. So during the 30-minute wait, you can go on to the next phase of the experiment. It's been about 30 minutes since we've collected our wet calcium iodate precipitate, filtered it, and put it in some water. In this case, we put it in 40 mils of DI water. Here we put it in 80 mils of DI water. The next step is to actually collect the filtrate. The filtrate is the stuff that comes at the bottom. Now in your protocol, the collection receptacle was a beaker. I just used a Erlenmeyer flask. Basically anything that is convenient or anything that has your funnel that can fit. So in my case, the funnel fit into Erlenmeyer flasks. You can use a beaker, whatever receptacle you will use to collect the filtrate. It's important to note that in this part of the experiment, we want the filtrate to be free of water. So when we collect the precipitate, we want to collect it in a condition that is as dry as possible. So just a little bit into the theory of what we're doing here. We don't want to add water. Let's make this as dry as possible. And let's just collect this. I did not wet my... Let's do this for the precipitate that was in the 80 mils. In a dry piece of filter paper. You want all your glassware to be as dry as possible. And of course you want your filter paper to be as dry as possible as well. Here. You can use a spatula as well. I'm using a glass rod. So it's important to realize why you are making this, or collecting the precipitate in a dry filter paper and dry glassware. Remember, you are measuring the solubility of calcium ion and iodate ion in calcium iodate. And this calcium iodate precipitate that you collected is sparingly soluble. So when you filter it, you not only have your solid calcium iodate shown here, but what is in the filtrate? The filtrate contains your calcium ion and your iodate ion. Both, whether you put that precipitate in 40 mils or whether you put that precipitate in 80 mils. So it's this filtrate that contains the calcium ion and the iodate ion. You will react the iodate ion with potassium iodide in acid solution and titrate that with the thiosulfate that you've standardized in the first part of this experiment. So it's important to realize the addition of water will actually mess up the solubility and change the equilibrium dynamics. Here is my filtrate containing calcium ion and iodate ions. I'm ready to perform my titration. This is the leftover precipitate. We can put that aside. We're concerned now with how much of this iodate will react with the sodium thiosulfate that's in my burette. So you can see here that I filled my burette up to the 0.00 mil mark, all the way to the top on for my titration. So it's important here to realize that we are going to do 4 titrations here. We're going to do what is called an approximate titration, and then after that we will do what's called an exact titration. The approximate titration is when you will take about a mil at a time of your titrant until you get the color change. We'll then do what's called the exact titration. In the exact titration, you will go 1 mil before the equivalence point from what you obtained in your first titration, the trial titration, and then right at that equivalence point, maybe a mil or 2 mils before, you're going to go drop by drop. So 4 titrations are going to be done. You're going to do an approximate titration, an exact titration. That is going to be from the precipitate that was dissolved in 40 mils of water. And then you have your precipitate that was dissolved in 80 mils of water. That was filtered. That filtrate, you will do an approximate titration as well as an exact titration. So this is the filtrate that I've collected after filtering my calcium iodate precipitate. This was precipitate that was dissolved in 40 mils of deionized water. So what you will do is you will pipette 10 mils of this. I've already pre-rinsed this with some of the filtrate. You're going to pipette 10 mils of this into your Erlenmeyer flask that will serve as your titrant. So you're going to pipette 10 mils of this. I've already done that. So 10 mils of your filtrate, about 20 mils of water, and then you're going to add your potassium iodide pellets, about 1 mil or so. So you can just be approximate here. About 1 mil. So that's going to go in here. We'll add 20 drops of the HCl. Add about 20 drops of the HCl. About 20 drops. Now notice what's happening here. The IO3 minus from your precipitate that you filtered out from the filtrate has reacted with the potassium iodide pellets in the acidic medium, and now you get this color here. This causes the generation of I2 molecular iodine. To enhance the color, I'll just add 40 drops of starch. And here is my titrant. Now the only difference between this titration and the one you've done before with regards to the standardization is now the IO3 minus, the iodate anion, comes from your calcium iodate precipitate. Now it's important to realize what you're going to be doing here. You're going to be performing 4 titrations. So if we can go back here to our titrant, the first titration is what we will call the approximate titration. Here, you will just add 1 mil of your S2O3 minus titrant. You just add it 1 mil at a time in 1 mil increments, and you'll get a rough approximation of your equivalence point, where the color of this disappears. You'll follow that up with what's known as the exact titration. In the exact titration, you'll go about 1 or 2 mils before the equivalence point that you calculated in your trial titration, your first titration, and then 1 to 2 mils before that point that you calculated initially, you're going to go very, very slow, drop by drop, drop by drop. That will be considered your exact titration. All right, here we go. It's our trial titration. I have filled my burette up to 0.00 mils of my titrant, sodium thiosulfate. Here contains my filtrate containing iodate ion and calcium ion. The iodate is going to react with this. And I have my starch to label the iodine. Let's go ahead and do 1 mil at a time in our trial titration. So I can be kind of fast and loose here initially. So that's 1 mil. Okay, any moment now. I'm going to go 1 mil. Okay, so I'll read that, and I have about 29.13 mils. That is my trial titration, 29.13 mils. I'm going to do this again, repeat the experiment, and do my exact titration. Now what will my exact titration be? Everything will be the same, except maybe at around 27 mils or so, I'm going to start going very, very, very slow, drop by drop by drop by drop. So here's my exact titration. I already figured out from my trial titration roughly the equivalence point. So now all I have to do is go 2 mils below that equivalence point. So I can just dispense until I'm roughly 2 mils before the equivalence point. So that's why you want to do your trial titration when you do that 1 mil to 1 mil increment. You have that broad window to determine where the equivalence point resides. So from the 40 mil beaker of filtrate, you'll do the trial titration and an exact titration. This is what I'm doing now, the exact titration. And then the filtrate from the 80 mil beaker. Okay, you notice my color is beginning to change. And I'm almost at 2 mils. Maybe I'll just go a little bit before. Okay, here we go. I am roughly 2 mils. You see that I still have that very, very faint yellow tinge. And now I've got to be careful here. I want to go drop by drop until I remove that yellow tinge and it becomes completely colorless. So now I'm going to go drop by drop. And obviously the concern is overshooting. I think 1 or 2 drops should do it. Let's do 1 more. I'll quit while I am ahead, and I have my value for my exact titration. I'll note that down to 2 decimal places. And now I have a trial titration and exact titration, 2 values. You want to report your exact titration. Your exact titration is the number that you were very focused and very careful on getting in terms of the equivalence point. So record your exact titration for the 40 mil filtrate. Record your exact titration number for the 80 mil filtrate. And that will constitute 4 titrations. From that, you'll do calculations that are listed in your lab handout and your lab protocol to determine the solubility, S. From that solubility, you will plug it into your Ksp equation for calcium iodate, and from there determine the Ksp value of calcium iodate.